Log on, tune in, find out. Another good idea from Cambridge.
Yes, okay. Well, I'd like to thank the organisers for the invitation. It's a great pleasure to follow Don Berry. In my personal experience, he is the most useful medical statistician in the world. I will explain to anybody afterwards who wants to know. Okay. This is some of the talks in this conference, or many of the talks about clinical trials. This is going back to a much earlier stage of work, and it will define some of the quantities that Valery Fedorov used, for example. So here we are. These are experiments for enzyme kinetic models. That's where I used to work. That's the London School of Economics. Oh, have I said this is joint work with anybody? Yes, there we are. Sorry, this is joint work with Vashava, Gatska, Patan, and Kuresh Yudim. So a catalyst is a substance that takes part in a chemical reaction but is not itself consumed. Let's see if this. Yeah. So here we have a substrate, we have an enzyme, they form a complex, and it breaks up to give the product, and we should have the catalyst back here again. So it's like the Haber process. You put hydrogen and nitrogen, you pass them over platinum, you get a chemical reaction, but the platinum remains. So, interest is in the velocity of these reactions, and the typical one is the Michaelis-Menten model, and I will be talking about extensions to the Michaelis-Menten model. So here it is. This symbol here is the velocity of the reaction, and that is the quantity that is of interest. And the two parameters, the two parameters are the maximum velocity of reaction here and this velocity constant here. Okay, this is a picture then of the model. This is the response function, and you can see that as the substrate concentration increases, the velocity goes faster. The parameter here, this Km, is such that the velocity at that concentration of substrate, the velocity is half of the maximum velocity. The question is, at what values of substrate concentration should measurements be made to get good, that's accurate and inexpensive, estimates of these two parameters in our model? So to think about this problem, we need a little bit of optimum experimental design, which Valery talked about earlier. We require a model. Here is a typical linear regression model, so this might just be a quadratic in x in our case being the substrate concentration. You write this in matrix form like this, but in actual fact our models are going to be nonlinear models. Here's a very simple model. The model that we looked at a moment ago was slightly more complicated. Apart from requiring a model, we also require a design region for Michaelis-Menten model. We could have measure at concentrations of 0, well that probably wouldn't be very informative, up to some value S max. And when we get to these more complicated models with inhibition, the design region, the concentrations that you can measure at, has a large effect on the design. This is, you will remember perhaps from Valery's talk that here there were some Xi's. So these are the designs. These are the series of little n conditions at which we take measurements. Here we have the proportion of experimental effort that goes at each of the different concentrations. I won't be talking about them very much, but in practice, these are continuous. For the ease of the theory, these are continuous weights between 0 and 1. In practice, you'll have to put 3/7 of your experimental effort, or some ratio of integers at a particular point. And what I'll be talking about are going to be what are called continuous or approximate designs. There's an information matrix up here. X transpose X is what one tends to think about it in introductory regression. D-optimum designs, which I will be partly talking about, maximize this determinant, and the maximized determinant is this quantity here, m of psi star. Stars will be used to denote optimum designs. Mostly, they will be designs that maximize this determinant. In our comparisons, we will make use of design efficiencies. That's just the ratios of these determinants raised to the 1 over p power. So a design with an efficiency of 50% requires twice as many trials as the optimum design to give the same information about the value of theta. We will come back to that. It'll be important in an example. Another thing that will be important is this is what is called general equivalence theorem. This is a very ungeneral version of it. Here is the variance of prediction at a point x in our design region, and if a design maximizes this determinant, if it's d-optimum, then it also minimizes the maximum over the design region of this variance, standardized variance of prediction. That is more than just a sort of mathematical curiosity. In particular, we can check any purported optimum design. If somebody says to you, this is the best design that we can do using d-optimality, you can search over the design region and you can find out whether in fact the maximum of this thing is equal to p. Valeri called it a derivative function, which is probably the negative of that and so on. But okay, last bit of background on design before we get there. Our models are going to be at least partially non-linear. Expand the model in a Taylor series and then get this matrix of derivatives which have to be evaluated at some point. Evaluated at this talk at some point value theta naught, and in the linearized model the design matrix then will with f again, but these matrix of these derivatives, one row for each set of experimental conditions. This means that designs will probably only be locally optimum for nonlinear models. The optimum design will depend upon the unknown values of the parameters that have to be estimated. Okay, so that is a fairly quick tour of some of the tools that I will be using in the next few minutes. Here again is the Michaelis-Menten model, and as I said, the question is, at what values of the substrate concentration should measurements be taken? Well, here's our model. Now, here's a useful thing. D-optimum design, this is typical of the methods that are sometimes used and that will be used in our more complicated models. So D-optimum designs for nonlinear models with p parameters often have p support points, number of parameters. If that is the case, then we will have equal weight at each of the design points. So you could guess that the d-optimum design is of this form. Then the determinant has this simple form here because it's p by p matrix. So the algebra is quite simple. You can guess that one support point is at the maximum. It seems reasonable if you want to estimate this asymptote that you want to go out as far as you can, and then you can do some straightforward mathematics yielding an algebraic expression for S, for the second design point. But the assumption has been that we will have half at this point and half somewhere else. Is that the correct assumption? You can look at the variance function here. You can see there are two parameters in the model. It goes up to 2 at one design point, it goes down again, it goes up to 2 at the second design point. So this design then is locally d-optimum. This is the kind of procedure that we followed in building models for more complicated, designs for more complicated models. Okay, what is all this about then, having got the introduction? Enzyme inhibitors are molecules that bind to enzymes and decrease their activity. Since blocking an enzyme's activity can kill a pathogen, I think this is what happens in penicillin, the enzyme in that case is helping to build the cell walls, or it can correct a metabolic imbalance. Many drugs are enzyme inhibitors. And we've already had some mention today of giving more than one drug at a time. Many drugs are cocktails, and interactions may cause inhibition, or they may cause enhancement. This is a typical kind of diagram. So here, before we had substrate plus enzyme gives this substance which then breaks down to give the product, and we get the enzyme back. And here, in this particular model of competitive inhibition, you can see there is just a reversible reaction here, that this complex is formed and then it breaks down again. So this slows down. The effect of this is going to be to slow down the rate of reaction. So what I want to find then first is an optimum design for estimating the parameters in this model. Here is the model. The velocity equation is rather like what we had before, but there is now this extra term in here. So the same maximum velocity is obtained irrespective of the concentration of the inhibitor. As S gets larger and larger, of course, all of this becomes irrelevant. But the reaction will be slower for a fixed value of S. And V occurs linearly in the model. Where are we? There is V. So the optimum designs will not depend on its value. They will only depend on the values of these two parameters here. So we found some d-optimum designs. Well, this is actually really Matchepatan. He obtained analytical solutions to the design optimization problem for this 3-parameter nonlinear model. And as I say, he started off by conjecturing that the weights were of the form 1 over p. He found the optimum design, and then he used the equivalence theorem to verify it. And a further interesting point is that the design points are often on the border of the design region. There is the optimum design. What should you take away from this slide? You should take away, I think, two things really. One, V doesn't occur in these expressions for the optimum experimental conditions, because I say it occurs linearly in the model. And the other point is that you see these maximum concentrations occur quite a lot in these, or minimum, occur quite a lot in these expressions. Here is the d-optimum design. This is the variance function, this derivative function. Here are three, I don't know where they are, there, and there. Those are the three experimental points here, here, and here. You can see there the maxima. You can see that all of the points have at least some coordinates on the boundary of the experimental region. Now then, I think perhaps Basher then managed to organize the people at Pfizer to do two didactic experiments for us. The first thing was that a typical experiment that was used in Pfizer, they had 15 different substrate concentrations and 8 different inhibitor concentrations, and they formed a grid then of 120 points. And the experiment was performed and the velocity measured over this grid of 120 points. This was called a rich design. It's rich in experimental conditions, although France used this expression rich last week for those of you who were here, and I see her smiling now. It may indeed be rich in experimental conditions. It is poor in information, of course. It's not obvious from the picture, but many of the points of the design contribute hardly at all to the efficiency of estimation of the parameters. So it's rich in using up the shareholders' money. The Pfizer laboratories are closed since we since we did this experiment. So that's not. It's not. Cause and effect. What? I think these are very simple experiments to do. There's just this kind of thing, and you go with an automatic pipette or something. Okay. So So what happens? The rich design has a paltry d-efficiency of 18.21% compared to the d-optimum design. And we then, to show, I mean, we're all statisticians here. If Valeria stands up and says that d-optimum efficiency is 17%, 18%, sorry, we all believe it. However, in order to convince chemists, non-statisticians of this, we ran an experiment with 21 trials instead of 160, and this should have just about the same efficiency because this is 18%, and I suppose 18% of 120 is close to 21. These are 3 experimental points. We need equal replication of the optimum design. We had 7 experiments at each. And these are this is amazing, I think. I've never seen anything like this before. I mean, we all know about the theory, but this is a sort of just a simple practical example that shows it whole. Here you have the results from 120. Here you have the results from the optimum 21. And you can see the standard errors are really extremely close indeed. So this is, if you ever need to have an example that shows chemists or scientists of some kind that d-optimum design can really deliver for you, this shows it. And the results are entirely in line with the theoretically calculated efficiencies. Okay. We did a lot more things. We looked at the robustness of the designs. These designs are locally optimum. It's actually quite easy to look at the sensitivity of the designs to the assumed parameter values because we got analytical expressions. We don't have to do big numerical calculations or whatever. And the analytical expressions provide insight into the structure of the optimum designs. In particular, in this case, I mentioned before that many of the design points are on the boundaries of the experimental region. So if these are held constant, varying the parameters values in many cases doesn't have much or any effect at all. So this you can see from the form of the design that the efficiency does not depend, is not sensitive over quite a wide range of values to the values of the parameters. Okay, so that is these designs were found for a variety of other inhibition models as well. But in the remaining time, I'd just like to move on to talk about some problems that arise in model building rather. When I say not mathematical statistics, what I mean is in mathematical statistics, you start with a model and you deduce properties, and of course that's what we were doing for these finding these d-optimum designs. Here are a few problems that arose that they were of interest. One problem is that one 3-parameter model arises when 2 parameters in a 4-parameter model are equal, and chemists wanted to know how to design efficient experiments for testing the quality of these parameters. And another problem is they didn't quite know what the mechanism was. They had 2 competing 3-parameter models. How would one then discriminate between them? And we explored two possibilities, one involving d-optimality, the other t-optimality. Let's see how we do. All right. So this is the 4-parameter model, and this is the 3-parameter model. You can see when this parameter is equal to this parameter, you get this model. So the problem is, how do you design an experiment to test whether this one is equal to this? Well, you can rewrite the model, get it to look like that, reparameterize it, and this parameter here then is just the delta is just the to do with the difference in θ1 and θ2. And this then is the model that one gets, which reduces to 5 when delta equals 0. So the question then is, just want to design an experiment to see whether delta is equal to 0. So there in this table we have some designs, and we compare them. The first is the analytically known d-optimum design for the 4-parameter model. For the second for the second design, we keep the points of the design, but perform a three-dimensional numerical search to find the DS optimum design. We're only interested in delta, so we just want to look at that subset of the parameters. We can't find those analytically, so we have to find them numerically. This is the kind of thing that we get. So this is the D optimum design for all 4 parameters in that model. This is the DS optimum design using these support points for just for finding delta, and this is actually the DS optimum design. This is very curious, isn't it? There must be some analytical work to be done here. I mean, I calculated these to quite a high efficiency, and they came out to be these simple ratios of integers. My own experience of numerical work in optimum experimental design is you quite often get these funny things which are not always possible to find a reason for. Okay, so that's that part of it. The last part then, I would just talk about the other problem, which is it might be this model, it might be this model. Both models contain 3 parameters, so it's no good just designing experiments to estimate the parameters in the models. You will get designs with 3 support points. You won't be able to choose between the models. One thing that one can do is to combine the 2 models. The models are, I'm sorry, here's one model, here's the other. If you look at them, they have a bit of structure in common, and they're of this kind of form, where when lambda is 0 or 1, here we go. This is the combined model. When lambda has 1 value, you get one of the two 3 parameter models. When it has the other value, 0 and 1, you get the other one. And here is a parameter. It's important when designing experiments to choose between models. You're fitting them. You want to fit a model to a specific set of data. So the choices that you're making have to between models that are so parameterized that they will explain those data well. Okay, so you have to choose this value so it is coherent with any data that you can get. Okay, so I then found some DS optimum designs for estimating the value of lambda in this model. And what I then went on to do was to find some T optimum designs, and I'll then compare them briefly with the D optimum designs. So this combined model provides a method of finding the optimum designs for estimating the parameters of combinations. However, if only one model is of interest, T optimum designs maximize the non-centrality parameter of the F-test for departures from that model. What you really want to do, if you want to test whether a model is true against some other model, then you need a test, a statistical test of maximum power. And T optimum designs provide those. How well then does this DS optimum approximation work? Well, here's a little bit about T optimality. In linear models, you can form a combined linear model and test for the necessity of the extra terms. Do I want a linear against a cubic? Then I've got the second and third order terms that I can add. For nonlinear models, the situation is a bit more complicated. In our case, we've got 2 separate models, either one of which might be important, might describe the data, and we will find then 2 T optimum designs. T optimum designs say, this is true, how do I determine that that one is false? Asymmetrical. This is symmetrical, so I have to find some compound way of looking at the design. This is just stuff about T optimum designs. What you want to do is to maximize, there's a non-centrality parameter, the sum of squares of the true model minus the fitted model. This is just least squares estimation for the parameters in the false model. And here we are, here's the T optimum design for one of them. We've got 2. The T efficiency of one of them, of a design, is this quantity here, just the ratio of the non-centrality parameters, and we can combine these and look at the efficiency for two models. Here's the efficiency of some design for discrimination against one model, discrimination against the other model. Here is the form of this product form of the combined efficiencies, and one of the component designs will happen when kappa is equal to 0, the other when kappa is equal to 1. And typically what one does in looking at compound designs is to try to find something which has good compromise properties found as the values of kappa varies. You don't need to worry about these things. If you take logs in this criterion, you'll just get that the design criterion is of this form. And here we are. Here are typical efficiencies. These are the values of kappa going from 0 to 1. Here are the two T efficiencies for the compound T design as a function of kappa. Here are, if we use the DS optimum design instead, the one that I found to estimate lambda in the combined model, here are its T efficiencies. This is just a table to show that in fact these two, in this case, these two procedures are really well, you can see they give very similar designs. If you look at the support points of the designs, concentration of substrate, concentration of inhibitor, and the design weights are very similar. The efficiency of the DS optimum design is slightly less in both cases than those in the T optimum design, but they seem to give similar properties. Okay. So the compound T optimum designs and the DS optimum designs are close in support points. There is a little difference in this example whether you use one criterion or the other, and this is important because in some cases these T optimum designs you have to postulate a model, and then you have to postulate a design, and then you have to use nonlinear least squares to fit the model to the expectations from the other model, and this can be numerically tricky. Okay, that's this bit here, isn't it? Problem with these designs is they may be tricky to compute. However, the table shows in this case that DS optimum designs are slightly less good, but close, and the designs found here are locally optimum because they depend upon the parameters, and the question then is whether these T and DS optimum designs are close for all plausible parameter values. So here then is a summary of what I said. For parameter estimation, I've presented analytical expressions for 3 and 4 point locally D-optimum designs, and because of these analytical expressions, it was easy to explore the robustness of these designs. And then when I came on to model building, I talked a little bit about D1 optimum designs for the equality of parameters and a combination of models that provided DS optimum designs for model building. And then I looked at compound T optimum designs for discriminating with two models which are present on an equal footing. This is just for the record for those of you who will look at this again. Here are some references, but I'll go back to this. I think a final comment, really, question that I would like to ask you, is that we've just got two models here, and we look at one against the other and then the second against the first. If we were just doing a sequential experimental design, we would just put a design point where the fit each model to the data, and then put the next experimental point where the two models were furthest apart. That seems, of course, a much simpler procedure than here. What happens if you've got it's not unreasonable to have 10 models, so I suppose you would have, I don't know, 90 pairs of points, wouldn't you? There must be some surrogate procedures that are better. If there are no questions, I would value your opinion on what one should really do. Thank you very much for your time.
Anthony, thank you. I like very much your experiment with Pfizer showing them and but the question is, what are they doing now? Do they still do their design, or do they do some optimal design and or
I think
just a toy example?
The plan of course was that they follow the optimum designs. They were very excited about it.
Okay.
And they've done only few of them just to see that it really works. But then the time.
Yeah, the laboratory's been closed. I mean, the whole thing's gone, you know.
No, I thought it was a joke, but it was
No! You've been listening to Valeri too much. I mean, termination of his group is not a joke.
No, I know.
This has also disappeared. I don't know where he's gone. Switzerland somewhere, probably?
No, I don't know about it.
No, this is all ground to a halt suddenly. Somebody said they were transferring some of the clinical work to China. I don't know. Anyway. Yeah, it's rotten. Yeah.
Probably Byron Jones continues.
Yes, right.
And then my second question was,
Yes.
is that your approach? Their approach was more robust to any values of the parameters than your approach. So if they want to use it, how would you do that?
Sorry, which was robust?
Their approach, all the points everywhere.
Ah, yes. So you mean this is really what Valeri was saying, that you produce an optimum design as a benchmark, and then you need to produce some. Yes. Well, you need to think about what are what possible departures there might be.
Yes.
And then you need to formalize that, but it'll probably only be 2 or 3 more parameters. So surely you won't need 120 points, whatever you're doing. But I agree. Yes. Yeah.
In your competing models example, did you estimate lambda? And if so, might you have come to the conclusion that a better model would be in a combination of the two?
You might well have done, yes. Well, that's...
But did you estimate lambda or just...
Well, no, sorry, no. It wasn't... I can't remember now.
Okay.
Does this work?
It wasn't sure if you just searched too hard, you just choose lambda.
In that particular case, you're interested just in 0 or 1, but because those are the 2 models. But of course, if you want to design the experiment, you need to, and then you can get designs that are efficient for 0 or for 1 by looking at a range of values of lambda in the design. Okay. Yes. Thank you. Yes. Peter. Yes.
Wonderful talk. I don't pretend to have followed all the details, but
no, I'm sorry, I was a bit rushed, but there we go. Yes.
what occurs to me is sort of a very naive reaction that it might be worthwhile to write down prior probabilities on the models, make them equally likely, if you will. Then use standard Bayesian calculus to compute posterior model probabilities, or do it on the cheap using Bayes information criterion to penalize for a number of parameters.
Yes.
And then the problem then, it seems to me, would be that you have the kind of dual problem of designing to get a good estimate of posterior probabilities of models. And then in some sense, and I'm waving my hands, average among those, average the optimal designs among those. You want to design to choose models and...
Yes. If Don is still there, he could probably corroborate this. But there are, when I first thought about these things many years ago, there were problems on putting priors on models in which the parameters have different dimensions. Okay, because if you're trying to take non-informative things in spaces of different dimension, you can get anomalous results. I guess that's been sorted out.
Yeah, in fact, I did this. Actually, Kyle Wathan did this in the context of a group sequential phase 3 trial where the model is characterized by the hazard function. But the dimensionality of the model really doesn't matter.
No, it's not the dimensionality of the model, it's the different dimensions of the competing models.
Yes, that's...
I think that's the thing.
Yeah, and I think in the Bayesian world you'd use this reversible jump stuff. Again, I'm waving my hands.
Okay, well, thank you very much. Yeah.
I think you try not to be non-informative.
Sorry?
I think you have to be informative in your priors.
Oh, yes, okay, yes, yes. You can't just write down a non-informative priori. Yeah.
I
Okay.
can add something.
Yes,
So,
Valeria.
actually, I like that you raise this question. In my ancient book, when I was similar to Dawn, 12 years old, it was published approximately at the same period. So what is important, indeed, Anthony writes that it's invariant with respect to pride. When you select in non-informative pride, whatever, unfortunately it's non-invariant with respect to parameter transformation. And you really have serious problems when you have different dimensions to each model. So what we try to do actually to talk about only incremental information. So actually with Passman, and probably, and you remember this, with Passman we picked up Shannon information as a measure. So you have both unknown parameters, you have unknown probabilities of model, and then you can pick up Shannon information and look for increase of Shannon information. And the answer asymptotically was very simple. You have to place your next observation where discrepancy between models and their predicted corridors of errors in some sense is the largest one. Which intuitively similar to de-optimality. You place your next observation where corridor of errors for predicted response is the largest one. But we could not move further on because to prove some asymptotical properties of this nice procedure, we just failed. Since there, we never touched this subject. But this could be interesting to chat about.
Any further questions for Anthony? If not, let's thank Anthony again.